Hey guys, today we're going to work on related rates problems. The problem that we're going to do comes directly from your textbook. It's Chapter 3, Section 11, Problem number 11. It might also be helpful to open up to page 225 in your textbook. That's where you'll find the steps for related rates problems in a box at the top of that page. I'm going to follow those steps pretty closely, so it might be nice to kind of follow along. I didn't quite have room to print the problem and put the steps and do work, so I'll kind of talk through the steps if that's all right with you guys. So the first step of a related rates problem is to read the problem you're given carefully. So let's go ahead and do that together. A circle has an initial radius of 50 feet when the radius begins decreasing at a rate of 2 feet per minute. What is the rate of change of the area at the instant the radius is 10 feet? Okay, notice that I've underlined two things and I've also bold-faced one of the phrases. So let's kind of pick this problem apart. Underlined are all the relevant quantities that we're going to need to solve this problem. So that's that our initial radius is 50 feet and that the rate of the radius decreasing is given by 2 feet per minute. Okay, and also notice that in bold we have the rate of change of the area at the instant the radius is 10 feet. That's what we're trying to find in this problem. Alright, so we've read the problem, and now we need to make a sketch and we need to organize the information that we were given. So a sketch would look something like this, and this is a pretty simple sketch to make. We just have a circle, and it has a radius, and it also has some area. And over time, this radius is going to shrink. So maybe after a few seconds, or a few minutes rather, maybe our radius would be smaller, and then our area would be smaller. So the sketch helps give you kind of an intuition of what's going on in this problem. Now let's organize some of the information that we have. Okay, and again, this is kind of step one of our process. So let's say that we're given some things and we need to find some things. And we might not always use all the information we're given, so we're going to have to be really critical of kind of the information that we have here. So we know one thing for sure, our initial radius, I'll denote that as r sub initial, that's 50 feet. Also notice I really like to put the units when I'm writing this down and getting my information organized. Okay, also we know that our radius begins decreasing at a rate of 2 feet per minute. So anytime you hear the word rate in these problems, you should be thinking derivative. Okay, so if we have a radius that's decreasing, what that's saying is it's a radius decreasing over time. And so the way that we're going to denote that is dr dt. It's the derivative of the radius with respect to time. And this is not positive 2 that we can write here. It actually needs to be negative. So another key thing with related rates problems, if this was increasing, if our radius, that is, was increasing over time, then we would definitely have a positive 2 here. But we have that the radius decreases. So this is going to be negative 2, and this is in feet per minute. And we are asked to find the rate of change of the area, okay? So that, using kind of the same idea from the radius rate, right, we're going to write dA dt, and that corresponds to the change in area with respect to time. And we want to find dA dt when r of our circle is 10. So there's our information. So we've pretty much done step 1. So step 2, we want to write down any equations that are going to help us solve this problem. We know that the area of a circle is pi r squared. So the third step is to introduce rates of change by taking the derivative of the appropriate equations with respect to time. And in related rates problems, we're always going to be taking these equations, we're going to be taking derivatives with respect to time. So it's going to look something like this. dA dt, that's applying d dt to the left-hand side of our equation, equals, and I'm just going to go ahead and write d dt and pi r squared. Pi is a constant, So we pull him outside, and we're left with d dt of r squared. But keep in mind, r is changing over time. So really it's a function of time. So we need to treat it as a function. We can't just pull this down, this 2 down, and just say 2r. We need to do more than that. We need to use chain rule here. We're going to have pi. The 2 is going to come down. The r gets copied. But then we need the derivative of our inner function. And in this case, that's just r. So we're going to have dr dt. Also, just speaking in generalities, I mean, if you're given a dr dt, then we really hope that we're going to get a dr dt in our equation when we take the derivative. So if you don't have that, how would you plug in -2 at any point in this problem? So just intuitively, you know that you need something like this. So let's kind of clean up what we have really quick. We know that dA dt is 2 pi r dr dt. And in these problems, I don't like to use a prime and r prime. I really think it helps to use Leibniz notation here, using the dA and the dt, the dr and the dt. Because to me, that really says change in r over change in time. All right, let's move on to step 4. We're going to substitute our given values and solve for what we want to find. So notice we haven't used the fact yet that our initial radius is 50 feet. And as it turns out, we're actually not going to need it at all in this problem. So sometimes we're going to give you problems where there's going to be a little bit too much information. And that's okay. You just have to be able to pick through and find what you do need and what you don't. And that's why we organize at the beginning. All right. And I just noticed I did forget to write feet after that radius right there. So making sure that we're keeping track of units throughout the problem is going to be really helpful too. Okay, so again, step 4. Substitute given values and solve for what we want to find. We want to find dA dt when r equals 10 feet. So I'm just going to write dA dt equals. And now let's go back and let's really inspect what's going on with this derivative here. You have 2, that's a fixed number, pi, also fixed, r, and that's where we're going to plug in our 10, and then dr dt, which we actually know what dr dt is. So we can plug in both of these values at this step, and what we're going to have is the change in area of our circle with respect to time when the radius is 10 feet. So let's plug in both of those values at once now. 2 pi, that radius, which is 10, and that change in radius, which is -2. And when we do some multiplication, we're going to get that you have -40 pi. And we don't really want you guys to multiply the pi there. It's actually a lot cleaner mathematically just to leave it as pi. It's more precise too. And now you're step 5 here. So you have an answer, but in related rates, it's not enough just to get a number, circle it, and move on. We need to interpret what this means. So first of all, let's think about units, okay? So step 5, one of the parts of that step is to consider units. So we have area and we have time. So over here, we have to have area in the numerator of our units and time in the denominator. And so area in this problem is going to be given by feet squared. And our time, we've decided to measure in minutes. So our answer should be -40 pi feet squared per minute. And let's really quick, another part of step 5 is making sure that your answer makes sense in the context of the problem that you're working on. Okay, and it makes sense that we have a negative number for this rate because over time, if we decrease the radius of our circle, the area will also decrease. So the -40 pi makes sense intuitively. And so it might be good too on a test or even on homework to really quickly just kind of write a nice complete sentence at the end of this problem. This is the answer, but let's go ahead and really kind of try to interpret what we just found. So we found that the rate of change of the area when r radius equals 10 is negative, and Again, being sloppy with units here, when r is 10 feet, is negative 40 pi feet squared per minute. And that's our answer. No two related rates problems ever end up working out quite the same. But if you end up practicing these problems a lot, following the steps that you've been given, you're going to build up these intuitions of how to tackle these problems, and you're going to get pretty good at being able to solve very different kinds of problems using a really similar approach. So I hope this video has helped you kind of walk through what you need to do with related rates problems.